Okay, so that is the algorithm. Let's now look at why this algorithm is correct. I mean, we designed it, we kind of know the intuition of this, so you're probably already convinced that this is a correct algorithm, okay? But let's just do this more formally. In general, how do we convince ourselves that such a recursive algorithm is correct, okay? All right, so here is usually the typical steps you take, okay? Usually this is done by inductive thinking, namely you go bottom up. Okay, why do we do that? Well, we know that the algorithm, the way the algorithm works is that it started from an original problem, and then it breaks it into pieces and then recursively call the same algorithm down. Okay, so and when you break them into smaller pieces, you don't immediately solve it inside of that algorithm. So it's like that you call for initial algorithm, and then that may break the problem down into one or more pieces. In our binary search example, it's only one piece, but then you have to then solve each of the smaller problems. And then to do that, it's breaking it down again, the recursive algorithm, okay? And this process only stops when you reach to the termination conditions in the algorithm, okay? So when you reach a termination, that's when you can really finally, that's where you say, okay, for this little problem, I know how to solve it. So for the binary search, when your array is of only size 1 or 0, you say, now I know how to solve it. If it's 1, I just check, is that the element I'm looking for? If it's 0, it means I couldn't find it, okay? So those only at the most basic level, the bottom level, you know how to solve it. So to prove the correctness, you have to go bottom up. Okay, you first figure out what is the base case of this algorithm. Okay, that's step 1. Okay, and make sure that in the base case, when you solve it, we are doing it correctly. Okay, step 2, you have to convince yourself that as you continue to recurse down, the problem are getting smaller. Okay, because if it doesn't get smaller, getting bigger, then you're making this problem bigger and bigger. You will never stop. Want to get it smaller and smaller, that's when in the end you can terminate. You have to check that it terminates. Okay, instead of that your algorithm is going to have an infinite loop. Okay, so that's the second thing we need to check. Once 1 and 2 are done, you basically assume that the recursive, you need to check the recursive code, the idea is correct, and then you ask that if all of this are correct, give you the correct answer, does then the top level one also give you the correct answer? Okay, once that is done, now you see that basically we can just use this inductively. If all the bases are correct, that means the level above the bases are also correct. That means the next level is also correct. And when this level is correct, the final level is also correct. You just go bottom up. So that's inductive thinking, okay? But what we need to do is essentially these 3 key components. We have to figure out whether it works in the base case, whether the algorithm is indeed running on smaller and smaller problem and it will terminate. And then if the smaller problem is correct, that's the bigger problem. Is the whole algorithm also correct? Okay. All right. So let's look at the binary search example. It goes through the 3 steps. Okay. In the binary search, what is the base case? Well, base case means that there's no more recursive cost. You don't have to, because if there are recursive calls, you have to go down into that function. Okay. So it means there's no more recursive calls. You can solve the problem now. Okay. And if you remember the algorithm we have, the base case is basically, if you're here, then you have recursive calls. So the base case is when this happens. Okay, in this case, we say that, okay, we stop here. We're going to solve the problem either way. Okay, so these are the base cases for the binary search. Okay, and what we need to do is that to convince ourselves that in the base case, we solve it correctly. Okay, so let's just check. Well, if your current array is already empty, you don't have anything, that means I couldn't find it. So obviously, in that case, I need to return none. Okay. If your current array only has 1 element, so you already shrink yourself down to only 1 element here, where start equal to stop. Okay. What does it mean? I just check what is here. I just need to check this element. If this element here equals to t, that means we found it. Okay, we return it. Otherwise, because I mean, every time we assume that the element you're looking for is within this subarray. If this is not T, that means we couldn't find it, then we return none. So in either case, we're correct. Okay, so what I just said here is that we convince ourselves that the base case, in either case, we solve the problem correctly. Okay, all right. Now we know that in the base case, it's fine. Next is that you need to convince yourself your algorithm stops. It doesn't keep just getting into infinite loop, okay? So you said that's the procedure it terminates, okay? And what you observe is that in the code, every time you start with currently you have a subarray from start to stop, okay? And then every time you find the middle, and then now you either go to the left half or the right half, but either half is strictly smaller than the original problem, okay? So the array you're going to look at is getting smaller and smaller, strictly smaller, okay? That means at some point, it has to get to the point where the size of this array is either 1 or 0. Okay, so yes, we convince ourselves that the size of problem getting smaller and smaller, so the algorithm will terminate and the recursive calls are on smaller problems. Okay, so step 2 is also fine. Okay, the last step is the so-called inductive step, which is that in a specific call, let's say you just look at the algorithm itself. If you assume that within this algorithm, all the recursive calls all return correct answer, then does this algorithm at this level also return the correct answer? Okay, so now what we said is that for the binary search problem, okay, we just by design, if both this, if both this and this return, whichever way you go, whether you go to the left or you go to the right, if we know that the smaller problem, we guarantee to have correct answer, okay? Then by our design, we know that then this algorithm also return correct answer, because that's how we argued. We said that we check the middle. If your number is equal to the middle, we return already. If it's smaller than the one in the middle, then we go to the left, and then if the left is returning the correct answer, whether T is inside or not, then we return that value on. So this procedure also return correct answer. Same for the right side. Okay, so we now convince ourselves that if all the recursive calls are correct, then our algorithm indeed for that step will return correct answer. Okay, and putting all of the 3 steps together, we say that the entire algorithm, when you call binary search A, T, 0, and -1, will give you correct answer. Okay, because the base case is correct, and that correctness through the steps 3 propagate up till the end. Okay, so that's what we have. All right, we're going to see more examples like this idea later again. Okay, yeah, this is what we just said. Intuitively, you show by showing the base case, essentially you're showing that the algorithm works when the size is when the array size is 0, 1. Okay, then using the inductive step, if the size is 2, we know that that's going to be broken into 2 pieces, 1 each. And because the base case is correct, that means this is correct. Okay. Now, if your array size is subarray, size is 3 and 4, we know that when we break in the middle, that would give us pieces of size 1 and 2. And since these are all correct, this implies this step is also correct. Okay. And if now your subarray size is from 5 to 8, that basically means that when I break it into half, then the size will half of this array size would go from 2 to 4. Then because of this are all correct, all the smaller sizes are correct, that means that this is also correct. Okay, using the inductive step. Okay, and you continue and assume that your algorithm in the end is of size 2 to the k. Then using k steps, you can argue that your on the original array n, your algorithm is correct. Okay, so it's a bottom-up approach, this inductive idea. Okay, so this is the correctness of the algorithm. As what I said, we're going to see later that more examples of this inductive ideas.